So I've got the review document. It should be version 2. If I gave you the correct one, see, does it say down there at the bottom? Yeah, version 2. And I got some of them highlighted. So let's look at barium carbonate. Right, there's barium. There's carbonate. Barium is alkaline earth. Carbonate's 2- charge, 2+ charge. That's it. And what is it going to do? It's going to break up into these 2 ions. Okay. And the KSP, let's see, has a measured solubility. Okay, so the solubility is given, but the KSP is not. So if we write the KSP for this one, remember the solids don't count. We just use the barium at equilibrium and the carbonate at equilibrium. And we need to find out what that KSP is. So in order to do that, we've got to find out what the equilibrium concentrations of these 2 would be. All right, so I'm going to set up an ice table. So our initial concentrations, of course, are 0. But when the barium carbonate solubilizes, it loses a certain amount. And these are in concentrations, molarity. And the stoichiometry tells us that for every one of these, you get one of those, one of those. So that means we're going to add an S and add an S over here. Right? So really the only ones we're concerned with at equilibrium, this is just so we know what our symbols are and the ratio. So that's S, that's S. All right, measured solubility. Okay. That's the solubility. So this value right here is 403 times 10 minus 5, isn't it? Yeah, that's it. So if we plug that into this formula, that's going to be S times S, or S squared. We just need to square it. Okay. .03 exponent -5, and then the squared. So I get 1.62 times 10 to the minus 9. Should be the KSP. That agrees with the key. All right. How about this one? Uh-oh. This is not a good sign. But I need some furniture polish. Okay, number 6. The correct mathematical expression for finding the molar solubility of 10,2-hydroxide. All right, we're working from 10,2-hydroxide. And remember, in first semester, we looked at solubilities as black and white. So either is soluble or insoluble. And we came across the hydroxides, and all the hydroxides are insoluble, except for the alkali metals. But we're going to find out just how soluble they are. And for this particular one, it's going to make that ion and 2 of these ions. Okay. And the question is asking us, what's the molar solubility? So I'm going to set up an ice table for this one. And of course, we start off with 0. And if we lose so much of this one, it's gonna show up over here as the same amount. But over here, it's gonna show up as twice the amount. Okay, so we have S and 2S. And then the expression for the molar solubility, we need the, oh, okay, this is hypothetical. It doesn't tell us what the KSP is. It's just if we have the KSP, we can finish the calculation, but this is an intermediate step. So we're going to have 10(2) plus and OH minus squared for the coefficient. Then if we substitute the values, and 2S squared, and we resolve that, 2 squared is 4, S squared times S is S cubed. So we have 4S cubed. If we knew the KSP, then we could solve for the solubility. So D would be the answer for that. Who's next? Number 11. You know what? I think I'm going to have to shrink this one just a tad. Yeah, that's better. Okay. Which of the following compounds has the lowest solubility in molarity in water at 25 degrees? All right. If you're comparing compounds that produce exactly the same number of ions when they go into solution, then you can make a direct comparison between the Ks in terms of solubility. So the larger the K, the more soluble. But if and only if that first rule is in effect, like cadmium sulfide and calcium sulfate, they can be directly compared because they each produce 2 ions. Or let's see, aluminum hydroxide and silver phosphate would produce 4 ions each. They could be directly compared, but since we've got a mix, in order to calculate and compare the solubilities, we've got to go through the whole procedure. So let me start over here, give myself a bunch of room. A, B, C, D, and E. Yep. Okay, so here's where we use Henry Ford. Set up an assembly line. And we just did this one. Cadmium sulfide and calcium sulfate and aluminum hydroxide. All right, so these are going to produce this is going to produce 3 silvers. I'm going to leave the aqueous part out just for convenience. And 1 phosphate. This one's going to produce 1 tin and 2 hydroxyls. This one's going to produce 1 cadmium and 1 sulfide. And this one's calcium and sulfate. And the last one, aluminum and 3 hydroxyls. Here. Okay. So the pattern, actually, there is a pattern to the ice table when you set them up
if it's just the compound going into pure water, then the pattern is, and I'll use this as an example, right? If we have 3 silvers, we got a charge, and phosphate. And if one of these, if a mole of this goes into solution, what's it going to produce over here? 3 moles, right? Okay. It's going to only produce 1 mole here. So when we write the K value, the KSP for this one, it's going to be 3S cubed times S. So as long as we've got one of these, one of these, one of these, one of these, and I think that's typical. One of these, then the ratio is always going to be 3S cubed. So you got that 3 there and you got the cube there. All right, that's the pattern. All right, so we can write that one. The KSP is, let me write those in there, 1.8 times 10 to the minus 18. 3 times 10 to the minus 27. 1 times 10 to the minus 28. And 6.1 times 10 to the minus 5. And 2 times 10 to the minus 33. Okay, so when we set these up, right, this one is going to be 3S cubed times S, which is 3 times 3 times 3 is 27. It's 27 S to the 4th. Because you got an S cubed here and you got an S there. You got this one cubed, which is the 27. So this one's going to give us the same thing, right? You got 3 of these and 1 of those, 3 of these and 1 of those. This is going to be the same solution. And how about the others? Well, this one, these 2 are simple, right? You got 1 of these and 1 of these, so it's just S squared. All right. And this one is going to produce 2 S's, 1S times 2S squared. Right. And S times 2S squared would be 4S cubed. All right, so there's the solution for S. Now what is S for each one? That's what we're going to compare. All right, so for the first one, you want to divide this one by 27 and take the 4th root of it. 1.8 exponent 18 and divide by 27. And then my calculator doesn't have a root button on it, so I have to do powers to the 1/4. Right? If you take the 1/4 power of something, that's the same as the 4th root. And I get 1.6 times 10 to the minus 5 molar solubility. Okay. Now we're going to divide this one by 4 and take the 3rd root. And I get 9.3 times 10 to the minus 10. Okay. And this one, you just take the square root. Which is 1, I should have known that. 1 times 10 to the minus 14. And this one also is square root. 6.1 is 7.8 times 10 to the minus 3rd. And the last one is like the first one. 10 to the minus 33. Okay. Divide by 27 and take the 4th root.
9.3 times 10 minus 2. And I did something wrong. What did I do wrong? Maybe I punched that one in wrong. Let's try that again. Yeah, I did that one wrong. There you go. All right. So now all we have to do is compare the values. Which one is the most soluble? Well, that's not the same answer they got. So let me see, did I make a mistake here? 6.1 exponent minus 5 take square root 7.8, that was right. What this one? That one should be right. Right. Square root of 10 to the minus 28 is 10 to the minus 14, because square you get 10 to the minus 28. Which is fine, listen. Oh, read the question, right? Which one has the lowest solubility? Okay, that's the one with the lowest solubility. I was looking for the highest, and this is the highest solubility. But we had to go through all that to make that comparison. If we had, just to illustrate a point, if we were comparing just these two, they both make the same number of ions. And if we compare these two values, this one's higher than that one. This one's higher than that one. If we compare these, which have 4 ions produced, then we can compare this one. This one's higher than that one. That one's higher than that. But we threw a wrench in the gear with this one right here. All right, it's a different calculation. So we had to compare all of them by their true solubilities. That one took a little longer than I expected. So let's move along. Okay, number 13. The molar solubility of barium carbonate is 1.6 times 10 to the minus 9. And in this time, we're calculating the solubility. That KSP is the molar solubility no matter what. It doesn't matter what solution it's going into. That KSP is true regardless of the components of the solution. But the solubility will change. We want to know the molar solubility, molar solubility. We know the KSP. We know the constant. And that's constant based on temperature. So now we're going to put it in 0.1 molar barium chloride. All right, so here we have barium carbonate again. We're going to let it ionize in solution. And set up our ice table. This time we have a common ion. But chloride's not in there anywhere. Chloride is a spectator. Barium is 0.1 molar. So initially, concentration is 0.1 molar in that, and 0 there. So we know it's still going this direction because that's 0. So if we lose this one, we get one of these, and we get one of these. Now at equilibrium, we have 0.1. Let's see. Plus S and S. Okay. So the KSP is 1.6 times 10 to the minus 9. And that's equal to that one times that one. 0.1 plus S times S.
All right, we calculated the solubility, I think, originally, didn't we? Go up some more. Oops, too far. Measured solubility of 10 to the minus 5. And what we know for a fact is when there's a common ion already in solution, the solubility is going to be less. So this S is going to be very, very small relative to that value.
That means we can approximate 0.1, drop this one out, times S equals this value. So all we have to do is divide this one by 0.1.
So when you divide something by 0.1, it's the same as multiplying it times 10.
That means 1.6 times 10 to the minus 8
Equals the solubility. Why does it say 162? Oh, excuse me, I'm on the wrong one. Yeah, because KSP is only 1.6. Right, so, wait a minute, I'm looking at the wrong one. I'm 13? No, 13. None of these. Yeah, I was looking at the wrong one before, right? This one's not on that list. Right, it's not a given value. So none of these. Now there is one in there that assumes that the person working the problem made a mistake in calculation. Instead of dividing by 0.1, they multiplied by 0.1. And that would give you 1.6 times 10 to the minus 10, which is wrong.
All right, 13. That one.
Who's next? Let's try 17. Which of the following solid salts are more soluble in 1 molar hydrogen ions than in pure water?
All right. This goes back to the discussion of
How do we get slightly soluble salts in solution? I wouldn't even look at sodium chloride because it doesn't matter. It's totally soluble anyway.
there's carbonate.
There's potassium chloride is completely soluble. These are bad choices.
Here, how about this one?
There we go.
That's slightly soluble, and this is completely soluble. So really, what we're comparing, these are all completely soluble, each one of them. That's the wrong one, sorry.
So anything we do to them is not going to make them more soluble. Well, I guess I could think of a possibility, right? If you reach the saturation point, how do you make it more soluble? Well, how are the two ways that we can make things more soluble?
Well, one is add hydrogen ions.
When does that one work? All right. That one works
When you add hydrogen ions, it binds with the cation, the anion. If strong base.
So the anion has to be a strong base. And so each one of these, compare these two because
These guys are all soluble. We don't need to mess with those.
what's the anion here? Chloride. What was it formed from, theoretically? Hydrochloric acid, which is a strong acid, which makes the chloride what? A weak base. So we can't do that with this one. But if the anion comes from a weak acid,
That means it's a strong base. This one comes from carbonic acid, which is very weak. That makes this a strong base. And this one works for the hydrogen ions. All right. What's the other way? The other way is to add ligands for binding cation. Okay. And if we did that, if we added, say, ammonia, we could get this one into solution. So those are the two ways to increase the solubility of a sparingly soluble salt. It's all conditional. All right, now 17, 19. Let's say you have a solution consisting of 0.1 molar chloride, 0.1 molar chromate. You add 0.1 molar silver nitrate dropwise. Given the KSP for silver chromate is 10 to the minus 12, and that for silver chloride is 10 to the minus 10, which of the following will precipitate first? All right. So we actually have, we have chloride in our solution, right? Chloride ions, and we have chromate ions. Oops, is that right? Yeah, that's right. And they're 0.1 molar each. All right, that's given. And you had 0.1 molar silver nitrate. 0.1 molar nitrate. Now, first of all, is that going to precipitate either one of them at any point in the future? Possibly. Because silver chloride is insoluble, silver chromate is insoluble, relatively speaking. So which one's going to precipitate first? Well, we know what the KSPs are, right? They're given. So the KSP for silver chloride is 1.6, yes, times 10 to the minus 10. And the KSP for silver chromate, this is 2, is 9 times 10 to the minus 12. Okay. So how do we know which one's going to precipitate first? Remember the comparison you can make between the KSPs and the Q. If we can calculate the Q for each one of these situations, then we can compare that Q to the KSP and see, is it going to precipitate? All right, so this is going to be silver and chloride, and this is going to be 2 silvers. Well, silver squared and chromate. Okay. So we have, let's see, I'll be sure I'm not barking up the wrong tree. We're adding this dropwise. So at what point is the silver concentration in this one sufficient to exceed that value? So if we look at chloride, we can put 0.1 molar here and solve for silver. How about that? I think that's the way we need to go. So that means we divide this one by 0.1, which is 1.6 times 10 to the minus 9 molar. When the concentration of silver reaches this point, silver chloride will precipitate.
Okay, did I lose anybody? Okay. How about this one? If we know this one is also 0.1 molar, then let's calculate silver for that. So divide 0.1 into this value is 9 times 10 to the minus 11. Okay, so when the concentration reaches this point, the silver chromate will, oh, excuse me, my mistake. That's squared. So we need the square root of 9 times 10 to the minus 11. You see where I made that mistake? I was about to make a mistake. Because I forgot this right here. Square root, here we go. 1.4. 1.4 times 10 to the minus 5. That's not the right place for it. It should be down here. When that concentration reaches 1.4 times 10 to the minus 5 molar, it will precipitate. All right, so which one precipitates first? The one with a lower concentration, because you're adding it dropwise. So we're moving up from none to a little bit to a little more, a little more, a little more. When it reaches this concentration, silver chloride is going to drop out. And silver chromate won't drop out until the concentration of silver reaches 1.4 times 10 to the minus 5. By that time, all the silver chloride should be out of solution. And at that point, you may want to filter it, get the silver chloride out, and then hit it again. Continue your titration to get the chromate out. Okay? I don't see puzzled look, so I'm going to go on to the next one. This one, 21. Right. How many moles of calcium nitrate must be added to 1 liter of 0.182 molar KF solution to begin precipitating calcium fluoride? And the KSP for calcium fluoride is given there. All right, I added this little hint. At what calcium concentration does Q equal KSP? So let's set up our solubility. We're looking for calcium fluoride is actually the solubility equation. Right? And right, initially you don't have any, let's see. No, we do have some in solution, don't we? We have 0.182 potassium fluoride in solution. 0.182 calcium potassium fluoride. Potassium fluoride means that it's 0.182 molar, right? Because potassium fluoride is like that. Concentration of this equals the concentration of that. All right. You know what? I may be going at this, making it harder than it needs to be. If we've got 0.182 molar fluoride, and we know what the KSP is, 4 times 10 to the minus 11. That's going to be equal to the concentration of calcium. We did need the equation. And fluoride squared. Do we know what fluoride concentration is? Yeah. 0.182. Right? So if we put 0.182 in here and square it, then divide it into this, we'll know what the calcium concentration is at KSP. So if calcium exceeds that, then it will precipitate. Okay. Yeah, I was making this harder than it needed to be. Let's square that value. All right, so this is 3.3 times 10 to the minus 2. 3.31 times 10 to the minus 2. We'll divide that into 4 times 10 to the minus 11. Yeah, that's right. So calcium concentration, I would call it the trigger point. That is, when does precipitation start? Is at 1.2 times 10 to the minus 9 molar. So how many moles of calcium nitrate? If this is the concentration of calcium, and there's only one calcium for calcium nitrate, that means this is also the concentration of calcium nitrate. Is equal to 1.2 times 10 to the minus 9. It asks us for how many moles, right? In order to determine moles, you need molarity times volume. We got molarity. What's the volume? Volume's 1 liter, right? If it's 1 liter, that means the moles is equal to this. 1.2 times 10 to the minus 9 moles. Okay. I lose anybody on that one? All right. Let's go to the next one and see if I can mess this one up. Okay, 23. A solution is 0.1 molar in each. Lead 2 nitrate, manganese 2 nitrate, and zinc 2 nitrate. Solid sodium hydroxide is added until the pH of the solution is 8.5. Which of the following statements is true? No precipitate will form, only lead, only manganese, only zinc, and lead, or all three will precipitate. Okay, if we look at each one of these, they're the same. We can put an X in for each one of them. And since they're 2+ each, that means each one has hydroxyl. So this would be our generic, right? It'd be lead, manganese, or zinc. They're going to be the same, except in this equation, they're just going to have different KSPs. Oops, need to do that. 2 hydroxyls, and they're in solution. Okay. So, we also know the pH is equal to 8.5. So if we want to determine which of the following will precipitate, we need to know their KSPs. So if we say the KSP for each one, and let's see, let's keep them in order. This is lead, manganese, and zinc, right? Okay, 1.4 times 10 to the minus 20. And then 10 to the minus 13. And the last one, 10 to the minus 16. Okay. These are going to be equal to whatever this concentration is. So in this case, it'd be lead. And the hydroxyl is going to be whatever the hydroxyl concentration is, squared, right? Squared. So this would be manganese. This would be zinc. All right. So, a solution of 0.01 molar of each one of these. So 0.01 molar means what? It means this is 1 and that's 1. So this is also 0.01 molar. If we know this one, if we know this concentration, we know this value, we can calculate the values of lead, manganese, and zinc that it would take to precipitate. And then we can compare it to the actual value. Okay, so how do we get the hydroxyl? How do we get that concentration? No ideas. Let's ask Sorensen. 8.5 pH equals. Actually, let's make it easy on ourselves. What's pOH? 14 minus 8.5. Right? So this would be 5.50. Now the OH concentration is equal to 10 to the minus 5.50. Why is that? Because pOH is equal to the negative log of the OH concentration. All right, so we move the negative over here, and then we say 10, so that power equals this value. That's what logs do. So if I take 10 to the minus 5.5 power, let's see, here it is. I get 3.16 times 10 to the minus 6 molar. So now we know what the concentration is. 3.16 times 10 to the minus 6 molar for each one of these. Right? So in order to calculate the lead concentration, the manganese concentration, it says 2. And the zinc concentration, all we have to do is square this value and divide it into this one, and that'll give us the unknown. All right, so I've already got 3.16 times 10 minus 6 in here. I'm going to square it. 1 times 10 to the minus 11. So if we divide each one of these by 1 times 10 to the minus 11, that'll give us the value. Let's see. Let me enter that one several times. 1.4. Okay. Or divide. 1.4 times 10 to the minus 9. Yeah. Okay. I was just doing a mental check on my approach. So we divide this one by 1 times 10 to the minus 11. 2 exponent 13. Okay, that's 2 times 10 to the minus 2. 2 times 10 to the minus 2. These are in molarity. And then the last one. Let's see. Here, 2.1 exponent 16 sign. Flip it. Divide. There we go. 2.1 times 10 minus 5. 10 to the minus 5. Okay. So if we're going to predict whether one of these precipitates, this value has to be less than that value. In other words, we've got this much in solution. Is that enough? This is the minimum amount of each one of these that would cause precipitation. Right? And this is equal to, let's see, 1 times 10 to the minus 2. Right? Okay. So this one will precipitate when the concentration of lead is 1.4 times 10 to the minus 9. Yep, that'll make it. Easy. It'll start precipitating right off the bat. This one is less also. Right? This one, you need at least 2 times 10 to the minus 2, not 1 times 10 to the minus 2. You need at least that much to start precipitating the manganese. There's not enough. Right? So this one will not precipitate. That means D. Zinc and lead will both precipitate, but not manganese. Okay. Oh, this is an easy one, 24. We need, well, let's see, in the qualitative analysis scheme for metal ions, our analytical group 2 cations separated from cations of analytical group 3 through 5. We want a group 2 separated from 3 through 5. How do we separate this one from those? Okay. So you got a chart, excuse me, a schematic down here, I think. Yeah, here it is. All right. Get this out of my way. You guys can see it okay, but I can't. Okay. Group 2 from group 3. So group 2, you've already gone through the acidic stage. Now you're going to separate group 2 out here, this orange one, separate it from the rest. So how do you do that? Well, you add hydrogen sulfide. Okay. So let's go back up to 24. Oops, too far. All right. There we go. So add hydrogen sulfide to that acidic solution. It's already been acidified, so to speak, and you're going to form insoluble metal sulfides. That's the one. Right, so that would be C. It's just a matter of looking at the schematic to get the answer. All right, 25. Which of the following solid salts should be more soluble in 1 molar ammonia than in water? All right. This is none. Okay, how about sodium carbonate, potassium chloride, silver bromide, and potassium nitrate? Well, sodium carbonate is completely soluble in water. Potassium chloride is completely soluble in water, so is potassium nitrate. All right, so that's kind of a dumb question. The only one that you got left to consider is this one, because these are completely soluble. You're not going to increase their solubility by doing anything. So the question is, will ammonia increase this solubility? HBr is a strong acid. It produces a weak base. So acidifying won't work. That means we have to go the other route. We have to add a ligand. Well, and attack the cation. So is ammonia a ligand of silver? Yeah, we're going to play with it today in the lab. Okay, so that's really a no-brainer, given those circumstances. All right. 25. 27. Are we going backwards? I thought we already did one like this. The correct mathematical expression for finding the molar solubility of lead-2 chloride. Lead-2 chloride is going to produce lead-2 plus in solution and do better than that. 2 chlorine in solution. Okay, so using our pattern, when 1 mole of this solubilizes, you get 1 mole of that, but you get 2 moles of this. All right, so when we compare, when we write the KSP here, and we get the lead 2 plus, and we get the chlorine to the second power, then we substitute those values in here, S 2S squared, and we get 4S squared, which is 4S cubed for our final answer. So KSP should be 4S cubed, which is D. I'm not sure why, because we did one of those earlier. All right. Let's look at number 30. This is definition. Which of the following leads to the formation of precipitate when Q is greater than KSP? That's C. Probably should have done that one first. We've been using that rule several times. Okay. 34. Calculate the solubility of silver 2 chromate with a KSP of 9 times 10 to the minus 12 in 0.049 silver nitrate. All right. So here we have a common ion effect. Silver chromate is going to become 2 silvers and 1 chromate. Okay. And if we set up our ice table, we have an initial concentration of silver at 0. Oh, excuse me. No, chromate 0. Silver is 0.049 molar. Right? Why? Because silver nitrate is 0.049 molar, and each mole of silver nitrate makes 1 mole of silver, so it's the same concentration. Okay. So now we're still going to go that direction because that one's 0. That means we lose one of these, and we get 2 of these, and we get 1 of these. Right? Stoichiometry says 2 and 1, 2 and 1 out of 1. All right. So when we add them together, 0.049 plus 2S and then S. And our KSP is 9 times 10 to the minus 12 equals this concentration squared. Times this concentration. All right, now we have to decide, can we ignore this one right here? I think we can, because the solubility is going to be low in pure water. It's going to be much, much lower with this common ion in there. So I think we can do 0.049 squared times S equals this value. So if I square this one and divide it into that one, that should be S. 0.049 squared is 2.4 times 10 to the minus 3. And I divide that into 9 times 10 to the minus 12. And I get S concentration of 3, that's solubility, 3.7 times 10 to the minus 9. molar. That'll be C. Okay. Now, if we had the time, we could check to see if it satisfied the 5% rule, but I'm pretty sure it will. All right. 36. How many moles of calcium fluoride will dissolve in 3 liters of 0.049 molar sodium fluoride solution? Okay. Let's see. This is our solubility equation. Fluorides. And our initial concentration of fluoride is 0.089. Initial is 0.089 molar. We have none here. So that means we're looking for, first of all, we're looking for the number of moles that will dissolve in 3 liters. We need to find the molar solubility of this first, and then we can use the volume to find the number of moles. So if we say we're going to lose one of these, that means we're going to get one of those, and we're going to get 2 of these. 0.089 plus 2s. All right, so KSP, which is the same no matter what the solution is. All right, that's a constant. 4 times 10 to the minus 11 is equal to S and 0.089 plus 2S squared. All right. Now, can we say that this is going to be small? I think we can. We're going to say this is so small that it's actually 0.0898 squared. So I'm going to square this, divide it into that, and find out what the solubility is. 0.089 squared, which is 7.92 times 10 to the minus 3. And I'm going to divide that into 4 times 10 to the minus 11. And the molar solubility then is equal to 5.05 times 10 to the minus 9 molar. All right, so that's the concentration in this situation for the solubility of that compound. But this is only for 1 liter, right? If we multiply it times 3 liters, then we get the answer to the question, which is 1.5 times 10 to the minus 8 moles. Okay. Right. $37. Oh, here's another one. Okay, what's the best way to ensure complete precipitation of 10,2-sulfide from a saturated H2S solution? Ah, okay. Let's see, number 37. We don't even have to look at the schematic, because we're saying this is the only thing in solution. If we have a saturated solution of H2S, and it's going to produce 2 hydrogens and 1 sulfide, and we're trying to precipitate this solid,
right? And it's in equilibrium with 10, 2 plus, and sulfide, 2 minus.
How do we make this one as big as possible? That's the question. How do you make that sulfide huge? Well, you try to shift the equilibrium that way. Right? Make it go this way. So how would you do that? We can't add any more of this because it's saturated. So we got to approach this side, right? And we can't touch that because messing with this one, we can't add any more. So we have to focus on that one right there. So if we let Le Chatelier answer the question, how do we shift it this direction to make that huge? So it'll precipitate all this. We want to suck up the hydrogens. We need a strong base. Hydroxyl fits the bill. It makes water. Shifts the equilibrium that way, and you precipitate everything that's in solution. So the answer is add a strong base. Right? This would be my choice. I mean, you can pick other strong bases if you want. Anything that'll pick up hydrogens. We could put carbonate in there if you want to. Except the carbonate would probably precipitate 10 also. And then you'd have a mixture of compounds. This way, you get 10,2 sulfide and nothing else. All right. Let's take a look at 40. Number 40, the concentration of magnesium in seawater is 0.052 molar. Okay, I'll accept that. At what pH will 99%, say, 99% of the magnesium be precipitated as the hydroxide? Okay, so seawater has 0.052 molar magnesium ions in solution. Okay, we're given that. We also want to precipitate 99% of that. So why don't we go ahead and 0.99 and find out what that concentration is. 0.052 and 0.99. So this is 5.15 times 10 to the minus 2 molar. We want to take out that much. All right. At what pH will this happen? Well, if we're going to, the clue there is the pH. How are we going to precipitate this? And the other clue is they're giving you KSP for magnesium hydroxide. So they're telling you in this problem, magnesium hydroxide is the solid. Okay. So what are we going to get here? The KSP, right? One of these gives you one of these. And one of these gives you two of these. So if we write the KSP equivalence here, and the value is 8.9 times 10 to the minus 12. That's equal to what? That's this concentration squared. Okay. And let's see. And we know this concentration here. Right? That concentration. This is going to be our unknown. Right, so that S here, this concentration is given 5.15 times 10 to the minus 2 times, what's this? 4S squared. 4S squared. All right, so that value, this S value,
is our hydroxyl concentration.
No, 2 times that one is our hydroxyl concentration.
Right? This is going to be. There we go. The hydroxyl concentration is actually equal to 2S. So we substitute hydroxyl in there. And that's equal to 8.9 times 10 to the minus 12.
Right, so we can solve for OH.
Minus. It would be this one divided into that one, and then take the square root of it.
Okay. 8.9 exponent 12. And let's see, I'll flip these. And then, so that's
1.73 times 10 to the minus 10. I'll give you the intermediate step here. There we go.
then we'll take the square root of that.
Which is 1.31 times 10 to the minus 5 molar hydroxide.
All right, so how do we get the pH from that?
Negative log of 1.31 times 10 to the minus 5 equals
The pOH.
So I'll take the log of that, change the sign. This is 4.88 equals the pOH. And the pH equals 14 minus 4.88. .12.
Yep.
2. There you go.
That's the pH that will precipitate 99% of that concentration of magnesium. All right. Are we good?
All right. Yeah, don't inspire confidence.
.41. A solution contains 0.018 moles each of iodine, iodide, bromide, and chloride ions. When the solution is mixed with 200 milliliters of 0.24 molar silver nitrate, how much silver chloride precipitates out? All right. Okay, here's a case
Where we know the KSPs of each one,
each one of these.
the silver iodide, silver bromide, and silver chloride.
And the KSP of each one is given. These in the right order. Yeah.
1.5 times 10 to the minus 16.
And then 10 to the minus 13. And 1.6 times 10 to the minus 10. Okay. This is a case where you can directly compare the KSPs for each one to determine the order of solubility. Right? So, that means that silver chloride is more soluble than silver bromide, which is more soluble than silver iodide. That means when we add the silver nitrate to this solution, it's going to precipitate all of that. I think 0.18 moles of each one.
0.18 moles. Okay, we got that much of each one of these. Actually, we have this much of the ion, iodide, bromide, and chloride.
Okay. And we're going to add 0.24, 200 milliliters of 0.24 molar.
200 milliliters of 0.24 molar.
Correct?
silver. Now, why can I say that? Right, because for every one silver nitrate, you get one silver ion. So I can say this right here, 0.24. All right, how many moles of silver is that? Well, I can calculate millimoles easy, just 200 times 0.24. 200, 0.24, which is 48. 48 millimoles of silver. Okay. Notice also that the ratio here is 1:1. So 48 millimoles of silver is going to consume, let's just make it mole. What would it be? 0.048 moles. How about that? I moved 1, 2, 3. 0.048. So, is that right? Did I do that right? Yeah, 48 millimoles. 0.048 moles. Oh, okay. Hold on a second. Ah, no wonder it didn't make any sense. See my mistake? Nope. Decimal in the wrong place. There we go. Look at the problem. That's the value for each one of these. Now it makes sense. So if we say 0.048 moles of silver is all that's available, then we're going to use up 0.018 moles of that in this compound. Right? So now we have 0. But how much silver do we have left over? Well, we've got 0.030, right? 0.030 moles. Moles of silver remain. Now, the next one is going to take 0.018 out of that. Right? So it goes to 0. And what do we have left over? 0.012. Silver remain. Okay. And it's not going to consume all of the chloride left because there's not enough silver. Right. So when the question says how much silver chloride precipitates, it can only precipitate this much. So 0.012 moles of silver chloride precipitate. Okay, the answers are given in grams. So now we have to convert to grams. Excuse me. Moles on the bottom, grams on the top. So what's the molar mass of silver chloride? Well, let's see. Silver is 107.87 grams per mole, and chloride is 35.45. So that's 2, 1, 2, 3, carry the 1, 13, carry the 1 again. There we go, 143.32. There we go. 143.32 times 0.012. Is 1.7 grams. We get that much silver chloride at the end. Okay. All right.
Who's next? 41. 43. Oh, here's another group. When a mixture, let's see, when a mixture containing cations of group 1 through 3 is treated with H2S in acidic solution, which cations are expected to precipitate? Well, in acidic solution, analytical groups, H2S and acidic. Okay. Acidification will take out we'll take out group 1, and then group 2 will be taken out by H2S. So let's go back down. Let's go to the very back and verify that. Here we go. Okay. Acidification with hydrochloric acid will take out the insoluble chlorides, silver, mercury, and lead. Then you add H2S in that acidified solution, and that'll take out group 2. So actually, group 1 and 2 are taken out by this scenario, this step-by-step, acidify with hydrogen chloride. If you use nitric acid, it won't do anything, right? Because you're precipitating as chlorides. So you have to use hydrochloric acid first. Oops, too far. Let's see. 43, excuse me. There we go. So using HCl first takes out group 1, then H2S in acidic solution takes out group 2. That's D. All right. 46. All right. A cation M2 plus reacts with ammonia. M2 plus reacts with ammonia to produce a complex ion. And it does so in 3 steps. So we could look at this overall, or we could look at individual step, but what's the question, right? It's giving you 1 times 10 to the minus 3 mole sample of ammonium nitrate is added to 1 liter of 15 molar ammonia. Choose the dominant species. There's a lot of blue smoke in this problem, especially when they give you all these concentrations and the KB. To answer the question, all you have to do is look at that sequence of reactions. The first K is 10 to the minus 2. What does that mean? That means you're going all the way, excuse me, 10 squared. You're going all the way to the right. Then you're going to take that one and do it again. And that's even bigger. And then you're going to take that one and do it again. Add another ammonia. And that one is this one. So overall, you're going to end up with 3 ammonias and a 2 plus charge. That's the dominant species, because you're moving there, there, there. If we add all these together, and we multiply those together, we would have 10 to the, let's see, 2, 4, 5, 6, 7, 8. We'd have 10 to the 8th as our K value. It's going to be that one right there. And you don't need all that other stuff. Not for this question. Okay? 47. All right. What's the concentration of nickel ion in a 0.045 molar nickel nitrate solution? Let's see. Scooch it over so I can see it. Solution that is also 1 molar ammonia. Kf for nickel is that value. Okay. Okay. So what reaction are we talking about here? We're taking nickel and we're going to nickel with 6 ammonias attached to it.
So we got nickel in aqueous solution, and we got 6 ammonias also in aqueous, and that's in equilibrium with the complex ion. Also in aqueous solution. Okay, and the Kf for the formation constant here is 5.5 times 10 to the 8th. Okay, and that would be equal to the complex ion divided by the nickel concentration times ammonia to the 6th power. Okay. So far, I think that's everything, except we're given 1 molar ammonia and 0.05 molar nickel nitrate. Okay, so the nickel concentration initially is 0.05 0.05 molar is initial. And ammonia is 1 molar. Okay. And this would be 0. So what kind of change are you going to see? Well, all of this nickel is going to be consumed because what's 6 times 0.045? 3, let's see, 6 and 3, 24, 27, and 2, right? You're going to need this much ammonia, 0.27 molar ammonia, to complex all of that, right? So that means we're going to use all of this up. And at equilibrium, we're going to have that. Well, actually, you know what? This is one of those problems where you do the stoichiometry first, and then you do the equilibrium. So this is really not an ice table. This is a before and after. This is before, and this is after the stoichiometry. So if we use all of that up, what do we got left over here? Well, I should have kept my calculation. 0.045 times 6 is 0.27 minus 0.270 from 1 is 0.730 molar. Okay. And for every one of these, you produce one of those. So we're going to come over here, 0.045 molar. All right. This is the stoichiometry. Now we can go to equilibrium. Okay. So the equilibrium is going to take these values here, initial. We're going to say that's 0. This is 0.73. And this is 0.045. Right. Now what kind of change are you going to see? This time it's going to go back this way because that's 0. So let's see. Be sure I'm answering the right question. What's the concentration of nickel? All right. We're going to get some of this. Okay. Where does it come from? It comes from over there. Right? 1 nickel here, 1 nickel there. That means this one loses some. How about this one? If that one loses some, we're going to add 6 of these because the ratio is 1 to 6. Now at equilibrium, we have X here. We have 0.730 plus 6X. And here we have 0.045 minus X.
Okay, now we can go solve the equation. All right, so 5.5 times 10 to the 8th equals this concentration here, 0.045 minus X divided by nickel concentration, which is X, and ammonia concentration, 0.730 plus 6X to the 6th power. Okay. Now, I'm not sure if is X going to be large or small? Actually, X is going to be pretty small. We're not going to get a whole lot of nickel back from that reaction. I think what I did was I made the assumption that X was so small that we could ignore it. Yeah. Just checking myself. Okay. So if X is really small compared to these values here and here, this would be approximated at 0.045 over X times 0.730 to the 6th power. Okay, now we just have to solve for X. And it looks like X is in one place. So if I put X over here and put that one down here, that would be equal to 0.045 over 5.5 times 10 to the 8th times 0.730 to the 6th power. All right, 0.045 divided by 5.5, exponent 8, and then 0.73, enter 6, take that to the power, divide that in. So I get 5.4 times 10 to the minus 10. Molar nickel that remains in solution. Okay. And it turns out that X is very small, much smaller than this one or this one. So I think we're safe for that. All right. You all right? Okay. All right, 47. Let's see. I guess I can keep going until your lab partners get here. It takes a little longer. 50. The KF for the complex ion diamine silver 1 ion. That's the way you name that. Is 1.7 times 10 to the 7th. The KSP for silver chloride is 1.6 times 10 minus 10. Calculate the molar solubility of silver chloride in 1 molar ammonia. This is directly related to what we're doing today. Except this one gives you the KF. Yeah, and that's what we're going to calculate in the lab today. So we've got 2 reactions going on here at the same time in that solution. So we can combine these 2 equations. One of them for the complex ion, let's see, silver plus 2 ammonias is in equilibrium with this complex ion. Right, and the KF is equal to 1.7 times 10 to the 7. Okay, and then we've got, silver chloride is the solid that we're trying to solubilize.
There we go. So it's going into solution this way. And the chloride, yes, like that. And this KSP is equal to 1.6 times 10 to the minus 10. All right. So if we add these two together, the silver ions go out, right? You got silver on this side, silver on that side. So they don't come down. We do have silver chloride plus 2 ammonias yield complex ion in solution plus chloride ions in solution. Okay, and what's the K for this reaction? Multiply those two together. 1.7 exponent 7, 1.6 exponent minus 10. So this is 2.72 times 10 to the minus 3. Okay. Now, what are the other values given to us? Right, we have molar solubility of silver chloride in 1 molar ammonia. Okay, so we can set up an ice table. The molar solubility now is going to be a value here, right? Initially, you've got 1 molar here, and you've got nothing here, and you've got nothing there. So the solubility is going to be in terms of, we're going to lose one of these. And how many of these are we going to get? Same number. But if we lose one of these, well, we still only get one of these, right? Because it's one of those, one of these. But how many of these are we going to lose? Right? For every one of these, you lose 2 of those. There we go. So our equilibrium, that doesn't matter. Our equilibrium is 1 minus 2s. This is S, and this is S. Okay? So now we put this into an equilibrium expression. That's equal to 2.72 times 10 to the minus 3. So we have the complex ion. And here, plus, times the chloride ion. Those are both first power. And then over here, we just have the ammonia. Ammonia squared. Okay, now we can put our values in here, right? What's this value? Well, this is S. What's this value? It's also S. Okay, how about this value? It's 1 minus 2s squared. Okay, so what is S times S? It's S squared. So if you have squared in the numerator, squared in the denominator, that's the same as squaring the whole quotient. Okay, so the first thing we need to do is take the square root of both sides. Right? We got this value, we got this expression. If we take the square root of both sides, that gets rid of that square. So what's the square root of this one? Right, square root of 2.72 times 10 to the minus 3 equals what? I've already got it in my computer, so I'm just going to take the square root of 5.22 minus 2 equals S divided by 1
minus 2s. Okay. All right. So I've run out of room. Unless I just keep working my way over. All right, so for this one, we're going to have s on one side. We're going to have 1 minus 2s times this value. So 1 times that value is obvious. 10 minus 2. And then minus 2 times that value times s. All right. So I got to do 2 times that value. 1.04 times 10 minus 1. Minus 1 s equals s. Okay. Now we got to get s's on the same side. If I add this to both sides, then that's actually this is 0.104. That's the same. So on this side, it'd be 1.104 s. And the minus 2 equals 1.104 s. Now, s is simply this number divided by 1.104. Did I do that right? Yeah. .104 divided into that. There we go. 4.73 times 10 minus 2. Now to two significant figures. 4.7. Okay. That's a lot of work. I will admit. But the key to this problem is to recognize that these reactions are occurring at exactly the same time in the same solution, which means you can combine the equations. And let's see. What's next? 52. For the system, 500 milliliters of 0.02 molar manganese nitrate, manganese 2 nitrate, mixed with 1 liter of, I think that's 1 molar. Yeah, 1 molar. Sodium oxalate, C2O4 is oxalate. The oxalate ion, which is missing its charge, needs to be a 2 minus charge in there, acts as a ligand to form a complex ion with the manganese ion with a coordination number of 2. That just means that for every 1 manganese, there are 2 oxalates. That's all that means. So the first equation, manganese and oxalate, form manganese with a single oxalate with an equilibrium constant of 7.9 times 10 to the minus 3, or 10 to the third, excuse me. The second one is actually reversed. Notice that? If we take the first product, it is placed in the product position for the second one. It needs to be in the reactant side, I think, in order to get the correct K value. And when we flip an equation, what happens to the K? It's the inverse. You just invert it. Okay. All right. So the question, what are they asking? Find the equilibrium concentration O of the first one. All right. So let's this first ligand. I'm gonna leave the aqueous out of here because it gets in the way. The first ligand produces this one. And its K, its K1 is 7.9 times 10 to the 3. And the other one is backwards. So I'm going to flip it before I even put it up here. I'm going to put the products on the reactant side. I'm going to take that one. Then we're going to add another. And now we get 2 of these. That. Yep. Now the K would be the inverse of that value. The inverse of 1.6 times 10 squared. 1.26 exponent minus, take the inverse. So this value is going to be 7.94 times 10 to the first. All right. If we add these together, that means that one times that one. Shoot, be sure I'm heading in the right direction here. Yeah. So this one's going to cancel out on opposite sides. And our final equation is going to be 2 plus 2 of these. Will make this one. All right. And this is more than likely, right? If we go back to that original equation that said which is the dominant species, that's the dominant species for this reaction. But that doesn't mean there isn't still some of this left over. So we're going to have to come back to that one. What we have to do is find out what are the equilibrium conditions. Then we can go back and calculate this one, because that answers the question, doesn't it? What's the equilibrium concentration of this complex ion? So those two, that one and 7.9 x.3 times. This is 6.27 times 10 to the 5th is AQ. Okay, now, what are the initial conditions? Right. Manganese 2 plus went at the beginning. This is a stoichiometry and then an equilibrium, like that previous one was. So this is the beginning, or this is before. Let me put that. This is before, and this is after. So what's the concentration of the before? Well, let's see. We're given manganese, 500 milliliters of 0.02 molar manganese nitrate mixed with 1 liter of 1 molar sodium oxalate, right? What's the concentration of manganese? Well, we can find out the concentration of manganese is going to be equal to the molarity times the volume, gives you the number of moles of manganese. So we have 0.5 molar, excuse me, that's not right. Yeah, it is, liters times the molarity, which is 0.02 molar. This is the number of moles of manganese.
What's the volume? It's a liter plus a half a liter, right? 1.5 liters. So that's going to be the beginning concentration of manganese. 0.5 times 0.02 divided by 1.5. So this is 6.67 times 10 to the minus 3 molar in manganese. Okay, we can do the same thing for oxalate. C2O4. This is what we start off at. Right. So we're given 1 molar sodium oxalate. So if you have 1 molar sodium oxalate, what's the concentration of the oxalate? It's the same, right? Because for every mole of sodium oxalate, you get 1 mole of oxalate. So it's 1 liter times 1 molar. 1 liter times 1 molar divided by the same volume. Okay. So it's just 1 divided by 1.5. Let's see, where's my inverse key? Here we go. So this one is 6.67 times 10 to the minus 1 molar oxalate. All right, those are our beginning conditions. So if we work, okay, has everybody got that one? I'm going to put that over here. Let's see, maybe I'll squeeze it in. So we got 6.67 times 10 to the minus 3. And oxalate, we have 6.67 times 10 to the minus 1. Because I need some more room. So that was the stoichiometry for the reaction. We're taking it all the way to completion first. Then we're going to work our way back. So this, the initial concentration here is 6.67 times 10 to the minus 3. Am I doing this right? Yeah. You know, we're not finished. We were just calculating the concentrations. Sorry. So this was before. And there's more to it. Molar is 6.67 times 10 to the minus 4. 10 to the minus 1 molar. That was before. There we go. Now after, we're going to say everything reacts. So all of this reacts and we're left with 0. So for every one of these, you get 2 of those. So we need to subtract 2 times that value, 6.67, 10 to the minus 3 is 1.33 times 10 to the minus 2 subtracted from that value, which is 6.53 times 10 to the minus 1. All right, that's after. Now, what do we have over here? Well, for every one of these, you get 1 of those. So over here, after, I have to start with 0. Then after, we're going to have the same value that we left over here. Okay. All right, so those are the initial concentrations. Yeah. All right. But we're going to need a different. We're looking for this one right here. Here. So we have to use that equation. I think I got enough room to put it down here. Mn2 plus plus C204 yields MnC204. Okay, so now we build our ice table. Initial concentration here is 0. Initial concentration here is 6.53 times 10 to the minus 1. And initial concentration here, I messed up. Oh, that's the wrong equation. Because we've got concentration of this in there, right? And that equation doesn't have it anywhere. We need this one because that will give us this value. Okay, so we're working with a different. I know I thoroughly confused you now. We're using the second equation in its modified form with this K value. Okay, so now we have an initial concentration of, let's see, this one here, 6.53 times 10 to the minus 1. Initial concentration of this one, 6.67 times 10 to the minus 3. And we're going to say that this one is 0. So the change is going to be back this way. And if this is going to be, we're going to add some X here. That means this is the same ratio. We're going to add an X there. We're going to lose an X here. Let's see, this is 2. Hold on a second. Yeah. 1, 2, 1, 2. Okay, so this one's going to lose that much. Right? You know what? I think I'm making this harder than it needs to be. What is this K? K minus 1, the inverse there is equal to. It's this one. Divided by this one. And times this one. Here we go. Yeah. Okay, so we substitute in here. Let's see, we got this one 6.67 times 10 to the minus 3. And that's numerator. And this is our unknown. I'm just going to put an X there. And then we have this value, 6.5 to 10 to the minus 1. And this is 7.94 times 10 to the first power. All right, so all we have to do is multiply this one times that value and divide it by this one, and then invert it. We got X. Or we can put X over here, say 7.94 in that place, divided into this, divided into that. And we should get 1.3 times 10 to the minus 4. And that would be the concentration of that one. Solution. I don't know about you, but that makes my head hurt. That looks like a good extra credit question. Thing about extra credit questions though is you gotta show your work.
All right. Yeah, we're. Oh, no, we got till 10:30 done. Okay, and then we start the lab. Okay, we're good. 53. All right, what's the molar solubility of lead 2 chromate in 0.055 molar sodium thiosulfate? That's the name of that compound. And it gives you the KSP and the KF. All right, so we've got two reactions going on here. I'm pretty sure that's the approach. Yeah, we got two reactions going on here. One is the solubility of lead chromate, and the other is the formation constant for the complex ion. So I'm going to put the complex ion first. So we get lead 2 plus the thiosulfate. So how many of those do we need? 3.
Is in equilibrium with this complex ion. 3. We have 3 of them, and then 6 minus and 2 is 4 minus. Aqueous. And the K F for this one is 2.2 times 10 to the 6th.
Okay. And now we have the solubilizing of
Lead 2. Oops. Is that right?
Yeah,
Chromate. Now we get lead 2 plus and chromate 2 minus. And the KSP for this one is 2 times 10 to the minus 16.
All right, now we can combine these.
Everything's happening in the same solution. All right, the lead's going out. And we're going to have lead chromate solid plus 3 S2O3 minus yields. And I'm leaving out the aqueous parts. Complex ion and chromate. Well, this solution is probably bright orange,
Be my guess.
Okay, so the K value is going to be those two.
Multiplied, the product of those two Ks.
Which is 4.4 times 10 to the minus 10. Okay, so the K of this reaction is better than that K by 4 orders of magnitude.
So I guess that's a good thing. All right, so what are the conditions here? For what's the molar solubility?
All right.
So if we say that the concentration of thiosulfate is 0.055 molar, right? Because for every one of those compounds, you get 1 thiosulfate.
So this is the initial concentration of 0.055 molar. And you got nothing here, nothing here. And this solid is going to give up some, its solubility. And how much of this is it going to lose? We're going to lose 3 of those for every one of these. We're going to get 1 of these. and we're gonna get one of these. Right, so at equilibrium, we're gonna have 0.055 minus 3s, s, and s. Okay? So, 4.4 times 10 to the minus 10 equals this one times this one, right? S times S divided by this one, 0.055 minus 3s to the third power. Now, can we say that this one is going to be so small it's insignificant compared to 0.055? Yes. So that means this is s squared divided by 0.055 cubed. All right, now we don't need to say equal here. What we need to do is cube that and divide it into this. 0.055, which is, this is 1.66 times 10 to the minus 4. And we're going to divide that into this value. And so s squared is equal to 2.64 times 10 to the minus 6. And S, or the molar solubility, is the square root of that value. 1.6 times 10 to the minus 3 molar. Oops. I did something wrong. What did I do wrong? Oh, I know exactly what I did wrong. Put it into it should be the square root. 3.64 times 1.6 10 to the minus 3. Okay, something went wrong. Oh. I think I'm losing my mind. You do simple math. All right, this cubed is right, but that has to be multiplied by this. Six. Now, square root of 7.3 times 10 to the minus 14. 2.7 minus 7 all this. Okay. Any more? Nope, that's it.